So thanks so much everyone for having me here. We are here to talk about the mobiles. My presentation was for 20 minutes as I was told first, but I noticed that we have 12 minutes now, but that's fine. Mobile is a controllable, self-powered, wind-opportunistic sensor, a spherical sensor that can monitor the Arctic. We believe that it is going to have a revolutionary kind of effect on the information that we get about the polar regions. And I say why in a minute. For of course, the ice melting in all polar regions are in a alarming rates. For example, we have uh, um, in the Antarctica and also Greenland, the rate of ice melting has been tripled over the last 2 decades. And this is going to impact the regional situation and climate as well as global climate. So, especially in this crucial time that it's so. On the other hand, we need to see what are our options in the Arctic or Antarctica, in the polar regions, regarding the monitoring system available. So we have a series of fixed sensors and base stations that are extremely expensive, and not many of them, because of the harsh environment, no one can actually go there and change the batteries, or they're going to be covered by ice or snow in a single snowstorm. Someone is going to actually go in there and wipe the instruments, change the batteries, and on the other hand, we don't have even that many of them. Many of them they use solar cells. We have 6 months of dark season. That means it's not going to work. And in a very harsh environment, no one going to even send someone to get the information. What are our other options? Of course, we have remote sensing. Remote sensing is when you send an orbiter, a satellite, with a remote sensing instrument, so get information from the polar regions. The fact is that there are the information they can get is very limited. They usually is okay. They might get some information about ice mass, but not it's not even they have to get more information in the summertime because they're going to compare the water and ice level. So that means in wintertime, it's not going to work that well. And also, they're extremely expensive. For example, we have ISAT-2 is $1 billion. That's how they get the information, and it's only ice. There are many factors in the polar regions and ice that is not even remote sensing cannot help. For example, CO2, different kind of gases, different radiations. These are not something that remote sensing can get the information. So if you talk to the scientists, because I used to work at JPL, used to interact with scientists, I noticed that there is a huge lack of information, even wind on the surface. For example, I went asked them, hey, I want these mobiles to be wind-driven. What's the speed of the wind speed on the surface? They told me, oh, we thought you are going to tell us because we don't have this information. They have like 10-meter height. So anyways, on the other hand, for even remote sensing that is going to survey the ice mass, they still need some kind of ground truth sensor. They call it ground truth, meaning that their instruments need to be calibrated by the information that they get directly from the ground. And if you don't have such information, that means that even remote sensing is not that effective. So that is the situation, and what we are suggesting now is the Moball. So Moball is a multi-functioning spherical sensor. So as you see here, we are envisioning, you can envision, it's interesting when you talk about sensors these days, you're talking about making them smaller and smaller to nano sensors. Or this sensor is actually 2-meter tall spherical shaped sensor. So we have is a sensor platform. You can imagine it like a bouncy beach ball with a platform kind of that. You have all different kind of sensors, spectrometers, communication parts, avionics, imagers, camera. Most of them could be laminated inside the surface, the shell. We have a large cavity inside, and this is a wind-driven sensor. So before I go, okay, so for this is a design that we had for the mobile. So you can imagine that, first of all, this is a controllable system. So we have a dual functioning mechanical control and energy harvesting system that is hexaaxial magnetic wave in the middle. As you see, we have two layers. One layer, for the shell, we have an elastomer that is going to made of very nice material like ETFE that are going to be sturdy but light enough that they can go up down to minus 150 Celsius, that cold, and so those are the materials we're using, and we have all the sensors laminated inside the shell, and you can see that you see how those little kind of tubes that we have, and those are the opening of some of the sensors that we are using. So we are going to take advantage of wind in the polar regions. For example, this is the Arctic region. You see, for example, the wind of 3 meters per second is almost 100% of the time everywhere in the Arctic. The wind of 6 meters per second and higher, many areas are 90%. So the fact is, almost all time in the Arctic, in polar regions, either Antarctica or Arctic, we have wind, and we have a strong wind. And the fact is, the warmer the Arctic gets, the wind is going to be even stronger. Actually, that has a negative effect on the ice melting because it's going to push the ice pieces towards the warmer ocean. So that's another problem that it causes. But the fact is that we are going to take advantage of wind for our mobiles. So you can imagine that you have a wind-driven ball that with all these sensors, and they're going to go everywhere in the Arctic. They're going to scan the area. This is a sensor network. So the mobiles have peer-to-peer communication. They also have communication with the base station. That is going to make a wireless mesh network. And there's a strength in this architecture. This year, I'm not going to talk about the networking part of the mobiles. Perhaps next year, I'm coming back for the networking. And here we have, remember when we talk about the remote sensing, we said we still need some ground truth sensors in order to calibrate the remote sensing instrument. Mobiles can be used as a remote sensing instrument for airborne or spaceborne satellites instruments. So we are going to take advantage of the recent low mass, low power electronics. For example, all these sensors is libelium. I should have written actually. Okay, so there are libelium sensors that we have used. For all these sensors, it's less than a watt. On the other hand, for avionics and controllers, we have 5 to 500 milliwatts of power. So so that's how we believe that we can integrate several of these sensors inside the mobile and increase. This is actually unprecedented. They never, for the polar regions, no one got all this information like CO2, because again, remote sensing was not able to help them on those things. So anyways, so how we control the mobile? So we said that, okay, this is a huge area in the polar regions, it's windy. We deploy the mobiles and they go by wind. The fact is that the wind situation is going to be very chaotic, meaning that it's in one direction and next day is another direction. That helps the mobiles in order to scan the area. On the other hand, we are going to passively control these mobiles by studying the wind index. For example, if you in the polar regions, for example, if we want to deploy the mobiles in some area and you know the exact, kind of estimate the percentage of time that we have this kind of wind, we are going to, the mass and diameter of the mobile could be customized in order to say that what's the percentage of time that the mobiles are mobile. Because you can say that, for example, if we, if we customize the mobile, the diameter and mass based on 6 meters per second, that means this one. That means that the mobiles are going to be 90% of the time mobile in those areas. On the other hand, in an active way we can control it. We have two novel mechanical control systems. One of them is hexaaxial mechanical control. This one is dual functioning system, meaning that these are magnetic weights. So when the mobiles are tumbling around by wind, and these magnets are going to go around, these tubes are cold. So they're going to move or oscillate in the tubes, and they're going to harvest power, just like shaking flashlights. On the other hand, as soon as you want to get a control of the ball, you are going to get a control of these magnet weights to lean it towards right, left, or bring the mass down in order to stop it or make it slower. The other mechanical control system we have is a phase-changing pendulum, is this one. Briefly, I can say that this is going to be, first of all, this is the first pendulum, all the other pendulums in the world. You can change the angle and you control the structure they are controlling, like a sphere. On the other hand, what we have for the mobiles is you don't only change the angle, you also change the height, which is very appropriate for the windy areas. So on the other hand, in a distributed way, we can control the mobiles. We have different regions with different priorities. Because we can mobiles have a stop and go capabilities, we can make sure that they stay in a region, and we can even control the density of the mobiles in different areas based on the strategic value of those systems. So that was our field testing of the mobile. The first system we had at the time I was at JPL and Caltech. Anyways, so this is a rigidized structure. We don't use air pump. That's how you see how the zipper is open here? That means that we don't need power to inflate the ball. This is our prototype of the energy harvesting system. And the very nice design of it that Professor Junichi Asama did for us, that it is going to optimize the energy harvesting because of this making this parallels, and the power that we have for one single unit was 1.5 watts. For 6 of them was 12 watts, and in a you could have 120 watt hours per day, which is more than enough. Imagine for the communication with the satellites, we only need 0.8 watts. This work has been performed by late Dr. Alberto Behar in Greenland. These are the sensors we use, and that shows this is actually portal. So that means that mobiles were able to send the information to the satellite, and we got the information back. This is a peer-to-peer communication. We use Libelium. This is the proof of concept for that one, because that means that even for peer-to-peer communication, we were able to send some information and send it back to the other mobile they could detect it. Mobiles is important for summertime because we have puddles, water. They act like a drifter in the summertime. They can even use the same mechanical control to go in the water. We have the system is a distributed control system. because of they have this networking, they can share tasks, Moball can share tasks to optimize their resources and performance. They can learn from each other. And thanks to NASA for their support. Please, we don't have time for questions, or we do. Sure, thank you.